Okay, I guess it's ready or not. Here we go. We've got the last section of your calculus book. This is section 11.3, all about polar curves, or at least about as much about polar curves as we're going to need for the AP test. So let's get ready to go. Get your pencil, get your calculator. You're going to need both of them, and rock and roll. Okay, we start off by looking at the spiral graph thing. It's an old toy, admittedly. It was kind of old when I was a kid. But basically, if we can zoom in over here, we can kind of get the idea. You stick your pencil inside of a little gear here, and then you spin it around, and it guides you to make these really neat patterns. And I thought, what better way to start off our section on polar functions and by looking at things that go around and around and make really interesting pieces of art. So we've got one special example of a parametric equation, and that's really the way I want you to think about these. These are just parametric equations with a really well-defined parameterization. So this is x is equal to r cosine theta, and y is also equal to r sine theta. And that is called something in polar coordinates. Polar coordinates means we're going to transition away from x and y and toward a coordinate system that is r and theta. So we're describing things by, number one, how far away are they from the origin, which we're going to start calling the pole. That's r. And then secondly, what kind of angle does, if you draw a line segment from that point to the origin and then back out on the positive x-axis, what angle does that make? That angle we're going to call theta. So we're looking at coordinates that are described with r theta. Later on, we're going to take a look at r theta, and it's, how do I say this? It is superimposed really on top of the Cartesian coordinates. Did you know that it was called the Cartesian coordinate system after René Descartes? Maybe you didn't, but now you know. So in the figure above, we've got polar axis drawn radially with, I don't know what word that was supposed to be, but with radii drawn emanating from a central point called the pole. So that is the pole right in the middle. You may want to think about that. That kind of looks, no, that looks a lot like the graph of what you would see on the North Pole, where all of the lines of latitude are meeting, converging at that central spot right at the North Pole. Same thing happens at the South Pole. That's probably why we would call it the pole, don't you think? That red point over here, that has Cartesian coordinates 2, pi. No, I'm sorry. Those are the polar coordinates 2 and pi over 6, meaning this is 2 units away from the pole, 1, 2 units, and then the angle that it makes is pi over 6. So this angle right here is pi over 6. If you were to convert that to Cartesian coordinates, you would get the x-coordinate is root 3, and the y-coordinate is 1. Notice how that coordinate is in the first quadrant, and the Cartesian coordinates also confirm first quadrant. Okay, so we have a whole lot more there, and the conversion between polar coordinates and Cartesian coordinates happens like this. X is equal to r cosine theta, y equals r sine theta. This brings us to our first task, would be to convert the green coordinate, which is right here. Let's convert that into Cartesian coordinates. So let's go ahead and do that. We know that, let's use green since we're talking about the green coordinate. We know that r is equal to 3. I can see what that white rectangle was now. Ooh, I'm going to have to change a few things, right? R is equal to 3, and theta equals 7 pi over 4. That would mean that the x-coordinate is r cosine theta, which further, once we substitute, that's 3 times the cosine of 7 pi over 4. Well, what is the cosine of 7 pi over 4? That is positive root 2 over 2. So when you multiply that out together, you get 3 root 2 over 2. How about the y-coordinate? The y-coordinate is equal to the r multiplied by sine of theta. R is still 3. Sine theta is still 7 pi over 4, which is equal to 3 times, well, now what's the sine of 7 pi over 4? And we're in quadrant 4. So the y-coordinate is negative rad 2 over 2. So that gives me the Cartesian coordinate negative 3 root 2 over 2. So xy is equal to 3 rad 2 over 2, comma, negative 3 rad 2 over 2. So that's our first task. Here's what I was alluding to earlier. This is the polar graph superimposed upon really just regular graph paper. But you can see that as we go from a theta from 0 to pi over 2, we are in the first quadrant. Once we go from pi over 2 to pi radians, we're in the second quadrant. Pi radians to 3 pi over 2 radians, we're in the third quadrant. And then finally, fourth quadrant, if we get radian degrees between 3 pi over 2 and 2 pi, or 0, depending on how you want to think about it. So negative radii, how does that work? Well, over here, this is the example that we're really going for. That it has a coordinate of negative, or a theta of negative pi over 3. So what would that be if we turn that into a positive? Well, we're in, well, you should remember that since we are periodic in terms of 2 pi, if I just add 2 pi to that, 4 and negative pi over 3, that's equivalent to 4 and 2 pi plus negative pi over 3. Let's do the math on that real quickly. 6 minus 1 is 5 pi over 3. So that's, these two are equivalent. They map to the same location. Okay, so that takes care of how do I deal with a negative value here for theta. How do I deal with a negative value for the radius? Here's one. Negative 7, the angle is pi. You'll notice for this one that if I had graphed, well, no, this is a distance of 7 away from the origin, so that has something to do with it. If I went over here and I did 7 and pi radians, that would lead me to right here. That is 7 comma pi. So if I do negative 7 pi, then I need to go in the opposite direction, not in the positive direction, but in the negative direction, and that will get me to this one. Well, what is this coordinate if I made that theta positive? Well, if I made that theta positive, well then this coordinate, negative 7 comma pi, that's equal to positive 7 and then 0, which is 7 and 2 pi. So really what we can do here is that's the same thing as, or negative 7 pi, that's the same thing as 7, and then that degree pi minus pi, or 7 and then pi plus pi. So either of those work. If you have a negative radius, all you need to do is add pi or subtract pi, and you got yourself the coordinate with all positive radii and angles. So here we're going to start graphing this one, and the first thing to do is just to fill out this t-chart. I'll leave you to that. I'm going to do mine. So pause it here, and then we'll get back to you. So pause. So here we go. You've got the chart all filled in with our cosine evaluated at the standard angles in the first two quadrants. I'm going to plot that second one for you, and notice the first one's already plotted for you. The second one is at pi over 6 radians. I got the cheater over here. And then a radius of 3.7. So here's a radius of 3 going down, or I guess I should say up this radius. 0.7 should be maybe right about there. So let's make a nice fat point there, and too much pressure. Okay, 3.7. The next one is pi over 4 and 3.4, so that's just less than the halfway mark. Next one's pi over 3 and 3 exactly, so that is right here. So go ahead and do the rest of those. It gets a little difficult once you get close to the pole over here. I'm going to zoom in so that we can make this a little bit easier for ourselves. Too bad you can't do this pencil and paper. And then I'm going to connect these. Now the way to connect these when you're dealing with the polar curve is to connect them in the counterclockwise direction. So we're going to start here. We're going to try to be smooth about it, and we're going to get to this guy. That's the next one. Be smooth and get to this one. And then I'm still going counterclockwise. Still going counterclockwise. Counterclockwise. Oops. Counterclockwise. And then eventually we get back to the origin. So here is that. Kind of looks like we're doing a little bit of a spiral here, don't it? Spiraling in. Yeah, I know you see it. There's our inward spiral. Okay. Let's move on with our work. Here we go. We've got polar functions. You guys can read this all to yourself. I'm going to just highlight a few things. The first class of functions that we're going to talk about are limmason. When we graph polar curves, we don't really do what we did with the t-charts, where we just do each point individually. We just take a look at the general shape of the function. What class of function is it? And then based on the characteristics of that function, we graph the entire thing at the same time. Maybe we'll graph 2 or 3 points. I think with the limmason, I graph things on the positive x-axis, positive y-axis, in the negative x direction, and then the negative y direction. I graph those 4, and then I think you can just call those the cardinal directions. But I graph those 4, and then I know what the shape of a limmason looks like. These ones here happen to be called cardioids, or a cusp limmason. I think you can see where the cusp comes from. This is a cosine one. This one is also a cosine one. So when I see a cosine limmason, we're talking about ones that are symmetric about the x-axis. They have the cusp, or the little indented part, will happen on the left or the right side on the x-axis. If you take a look at the sine limmason, here's 1 plus 1 sine theta and 1 minus 1 sine theta. These are symmetric about the y-axis. So the curved part here, that's going to be on the y-axis. The other major part that I want you to notice is that the limmason is always thicker on one side than the other, and then it also has two sides, up and down. So the thicker side, generally, we'll take a look at that. The thicker side, well, sometimes we'll call that I like to call it a major axis. I don't think that's correct, but it helps me give a name to what I'm looking at. That would mean that the smaller side here, we would call that the minor axis. Again, I don't know if that's actual. And then the sides over here, we'll just call those the sides. How about that? Here's some more limacons. We got this first one. I don't know why the graph of the limacon is so thin there. It's kind of difficult. But if you see, this is 3 plus 2 cosine theta. And then the major axis goes all the way to 5. Well, where did that 5 come from? That's just 3 plus 2. So if you take A plus B, add it together, you get the major axis. How about 1? How do I get 1 from 3 and 2? Obviously, you just subtract. So the minor axis here will be 3 minus 2. Now, what about the sides? They're 3. So the sides are just the value of A. So if I continue to along the same lines, and I do this one over here, well, that's just going to be 3 plus 3. So here the radius is 6. Over here, the radius is 3 minus 3, which is 0, which is why that goes all the way to the pole. Up over here, A is 3, and that should make sense. That should be r equals 3. Likewise, down over here, r equals 3. Okay, things get a little bit dicey on the third one because we have 3 plus 5, and I'll show you where the diciness comes from. The first one is 3 plus 5. Sure, that's 8. The side lengths, that's just 3. A doesn't, or the B value of B doesn't matter here. And as an aside here, why doesn't B matter? Well, because at those angles, straight up and straight down, cosine is equal to 0. So it's, if you're looking at this, that's 3 plus 5 times 0. Well, what is 3 times 5 plus 0? Well, that's just 3. So when cosine is equal to 0, the value of the radius of the curve is just 3. But what happens over here, what is 3 minus 5? Yeah, I know it's negative 2. So that's why normally at pi radians, normally we would be out over here. But since we have a negative radius, we're going to come back on the other side. So that loop, that's really r equals negative 2. So follow this curve counterclockwise. Take a look at what happens. Counterclockwise, counterclockwise, counterclockwise. Well, what happens here? Do we jump over to this side? Or no, you don't. What happens is you do the loop now. So you go along the loop, and then you come out on the other side. Like I said, you keep on moving your pencil counterclockwise, just like you would on the spirograph. I know, you never played with a spirograph, so how would you know that? Well, that's what you do on the spirograph. So we've labeled those. Here are no, these are different observations. For the first of all, the greatest distance, I've been calling out the major axis. That's A plus B, we knew that. The sides of the limacon, that's just A. If A equals B, we're going to create a cusp. By the way, a cusped one is called a cardioid because it looks like a heart. Isn't that cute? It looks like a heart. If B is greater than A, then you're going to get a loop. If A is less than B, you're going to get a dimple or a flex. And that distance is going to be A minus B. That's our minor axis. Okay. That was a lot. I'm glad you can rewind and read that or listen to that all over again. Take a deep breath because we're going to move on to the next class of polar curves, which are called rose curves. Isn't that nice? You get hearts, cardioids, and you get roses. We should be doing this around Valentine's Day. Oh, my mistake. We have an example where we're supposed to graph the limacon first. So let's graph this. What's the major axis? Oh, no, first of all, is the major axis going to be north, south, east, or west? Well, it's sine, and it's negative sine, so it's going to be south. How long is that major axis going to be? It's going to be 3. So let's count 1, 2, 3. Here's how long the major axis is going to be. The minor axis is going to be 3 minus 2, which is 1. It's not negative yet. And then the side lengths are going to be 3. 3 and 1, 2, 3. My eyeball is playing tricks on me. So 3, yeah, 3. 1, 2, 3. Okay, so let's draw this cardioid. This isn't an AP graphing, AP. Oh, what did I do? I messed this up. Obviously not AP anymore because I made a mistake. That major axis is 5. Okay, so back to my current train of thought. This is an AP how to draw polar curves. So you don't have to draw a perfect polar curve. You just got to get close enough to be in business. Okay, is it going to dimple here? Is it going to flex here? I don't know. I like drawing them with dimples. And ultimately, it's not going to matter whether or not you draw it with a dimple. But I like the dimples. Then we'll go ahead and draw that. And then back out again. Radius is increasing until we get to back around. Okay, so there it is. No, it doesn't look like the best cardioid you've ever seen, but it doesn't matter. Good enough, I can do some calculations with that curve over there. Here are the rose curves, the ones that I've been talking about. This is lifted straight from your book, but some observations. First of all, a cosine rose curve always has this petal right on the positive x-axis. So that's going to be kind of important for us. We know that if we're going to draw a cosine curve, cosine rose, we better have that petal on the positive x-axis. The sine curve always starts with its first petal in quadrant 1. So that's good. And then the number of petals change their behavior depending on the value of n. So it says it all right here, but if n is odd, that means you have n petals. If n is even, that means you have 2n petals. If you get a chance, you should go ahead and graph that on your TI calculator in path mode. It's really interesting to watch how this goes around. Remember I said that the graph needs to keep moving in the counterclockwise direction, and that's exactly what happens here. It also is never going to make a sharp turn. Let's look at this one. How would this one move? Yeah, like that. So that's how that goes. And then once you've got those basic rules down, all you really need to do is figure out how to arrange the petals so that you're symmetric. Okay? All right, so let's move on. That's all we really needed to discuss here. Let's do this one. 2 sine 3 theta. So we need to figure out a way to figure out how many petals. Well, let's do that first. How many petals? N is 3. That's odd, so we have 3 petals. Good. A is 2, so the petal length is 2. So how do we have to have 1 petal over here, no petals on the positive x-axis. So how do I arrange 3 petals so I have 1 petal, at least 1 petal in the first quadrant, and we're symmetric about the y-axis? Well, that would look something like maybe like this. One down here, one in this direction, and then another one in this direction. Okay, does that look symmetric enough? Yeah, that does. So you know what I should have done here? I should have done all of that in my gray color. Here we go. This one over here, this one over here, this one over here. That kind of looks like we're symmetric around the axis. And then we'll just draw, follow along. And back to the other one. Always following the curve counterclockwise. All right. So is that good enough for me? Yeah, that's good enough for me. Okay. There you go. Here's our rose curve. Maybe I should zoom in on that. Let's zoom in on that. There you go. Rose curve. Maybe I should have made that petal length longer. What do you do? Okay. Last thing we're going to go over is a little bit of calculus. So we've got the slope, and this is really exactly the same thing that you would have done with parametric curves. It's just dy d theta over dx d theta. But it just so happens that the y-coordinate is r sine theta, which is why you see that r sine theta in the formula here. And the x-coordinate is r cosine theta, which is why you see the r cosine theta formula in the denominator for dx d theta. All right, one example here, Central Africa, the shape of the Snowpiercer's track is in the shape of a polar curve that looks like this, 2 sine 3 theta. Oh, so it looks like that rose curve that we just did. Find the slope along the track at theta equals pi over 6. Okay, let's see. So this is the slope, and that's equal to dy dt, d theta over dx d theta, which is equal to the derivative with respect to theta of r sine theta over dd theta of r cosine theta. Well, let's substitute the equation of r dd theta, and again, you are substituting an equation for r, not a value. So what is the equation for r? Well, that is 2 sine 3 theta multiplied by sine theta. And then what is the equation for r? It's still 2 sine 3 theta multiplied by cosine theta. Cap those off, evaluate this beast when theta equals pi over 6. Let me highlight where all this stuff comes from. R, that's R, and that's R. All of those things come from that equation for R that we just came from. Remember, R is not a value, R is an equation. Okay, so grab your calculator and chuck that entire thing in there, and we will see what we get. Okay, here's my calculator. Notice that it's not necessary to put r cosine theta, r sine theta there. I'm just putting the equation for r into y1. And then once I get to the home screen, okay, I have r sine theta on the numerator, evaluated when x is pi over 6. I've got r cosine theta, or the derivative of r cosine theta when theta equals pi over 6 on the denominator. Push enter, remembering that y1 is where I stuck the equation for r. Push enter, boom, negative 1.732. So the slope is m equals negative 1.732. So that means that the Snowpiercer at pi over 6 is moving in a direction that is basically downward, right? That's the slope of the curve. No, I shouldn't say it's moving. That's the slope of the curve that it's on. It's a downwards, down the slope. All right, let's take a look at the box. You can pause it here, and you will be able to get all of this stuff. It really is just a summary of what we were talking about. There is a lot of stuff here to memorize about the circles and the limaçon. I don't even think we talked about circles all that much, but those are pretty easy. I trust you could be able to figure those out. So pause it right here, and then I'm going to get to check your understanding. So 3, 2, 1. You should have paused it by now because we're going to check your understanding. So the first one, convert 2 root 3 into negative 2 root 3 into polar coordinates. Okay, so the first thing I want to look at is in which quadrant this is. This really is a little bit of a review of what we did. I think it was in 11.2. No. 11.2, 11.1, 11.1. So what is the radius is just the magnitude, which tells me that this is 11.2. So the magnitude here is equal to the square root of 2 squared plus negative 2 root 3 squared. So how much is that? Let's do a little bit of simplification here so I can ask Alexa what the answer is. That's like my favorite thing to do is ask Alexa math questions. 2 squared is 4. 2 squared is 4. 4 times the square root of 3 squared, that's 4 times 3, that's just 12. I don't even have to ask Alexa this one. 4 plus 12 is 16, and the root 16 is 4. I was hoping to ask Alexa. How about the angle? Well, theta is going to be equal to the arctangent. My bad, that's not theta. This is phi, the reference angle. See how it all came back to us already? The arctangent of the absolute value of the y-coordinate, negative 2 root 3 over 2, which is equal to the arctangent of root 3. So when is sine equal to root 3? Sine is equal to root 3 at pi over 3. We're in quadrant 4. I messed that up on one of the last videos. So sorry about that. Quadrant 4, so then our reference angle is this. So theta is going to be equal to 2 pi minus our reference angle, which is equal to, let's see, 6 minus 1 is 5 pi over 3. So in polar coordinates, 2, negative 2 root 3, that's equal to 4, and then 5 pi over 3. You can do it. It's not that bad. Number 2, let's turn this into Cartesian coordinates. X is equal to r cosine theta, which is equal to negative 5 multiplied by the cosine of 5 pi on 6, which is equal to negative 5. What is the cosine of 5 pi over 6? I think that is negative root 3 over 2. So the x-coordinate is 5 root 3 on 2. How about the y-coordinate? That's equal to r sine theta, which is negative 5 multiplied by the sine of 5 pi on 6, which is negative 5 multiplied by 1/2. That's equal to negative 5 over 2. So in Cartesian coordinates, negative 5 comma 5 pi over 6 is equal to 5 root 3 over 2, negative 5 over 2, coordinates, boom. Let's do some quick quadrant analysis, make sure we hopefully got that right. Let's see, 5 pi, we have a negative radius, so I'm going to subtract pi. No, I'm going to have to add pi. So 6 plus 5 is 11 pi over 6. So negative 5 pi over negative 5 and 5 pi over 6. I should write this down. Where is my mouse? Okay, here we go. Negative 5 and 5 pi over 6. That's equivalent to positive 5 and 11 pi over 6, which puts us in quadrant 4. Is this a coordinate in quadrant 4? Yes, it is. We are all good to go. Last one we're going to do here is we're supposed to, this is a long one. So is this video. We're at 36 minutes. Let's graph this. This is a limacon a plus b sine theta. So a equals 4, b equals 2. It's a sine curve, so we are symmetric about the y-axis. The major axis is going to go downwards because it's a negative sign. So our major axis is going to be a plus b, or 6. 1, 2, 3, 4, 5, 6. So here's our major axis. Our minor axis is going to be 4 minus 2, which is just 2. And the sides here are going to be 4. There we go. Is this going to be dimpled? Is this going to be, what's the word for it? Convex? I don't know. Let's just give it a really small dimple because, again, I like dimples. Dimples are cute. And is this good enough of a graph? Yeah, I think this will be fine. Lately, I've taken to graphing things kind of like if I was sketching, and I think that makes for a better product, especially when I'm doing this on a tablet. Okay, maybe it doesn't look like the most elegant thing out there, but it sure looks better than if I tried to do this in one go. All right, so this is my curve. Good enough. I keep on trying to polish that. How about, what is the slope at 3 pi over 4? 3 pi over 4 is right over here, right? So I'm taking a look. I'm thinking that this slope at 3 pi over 4, that looks like it's almost going to be horizontal. I'm not sure. I mean, depending on how I graphed it, if I graphed it correctly there, exactly correctly there, it could be a slight positive, slight negative. I'm not sure. So let's figure out what that slope is. M is going to be equal to dy dx, which is equal to dy d theta on dx d theta, which is equal to d theta of 4 minus 2 sine theta multiplied by sine theta on top of d theta, 4 minus sine theta multiplied by cosine theta. And I love highlighting things for you. So again, this is where R is, and this is R, and that is R. We're going to evaluate these guys when theta equals 3 pi over 4. And, time to pull out that calculator. So through the magic, here we go with our calculator. Notice that I went and I put in the equation of the radius 4 minus 2 sine theta, that's in y1, and going to the home screen, I've got the derivative of y1 sine theta over the derivative of y1 cosine theta, and all my calculator is waiting for me to do is push enter. So I'm going to push enter. Positive 2.92, so 29289. 29289. 29289. Did we predict that from our curve? Kind of. Clearly, this curve should have been going up still a little bit more, but that is that small value of a slope that I was talking about. So I think this is a win, right? It's a win. Folks, that was a long one. I'm glad you survived it. It's at 41 minutes. You've been here for 41 minutes, possibly longer if you've been pausing like I've been asking you to. But, you know, this is a subject that a lot of calc students are very uneasy with. Hopefully this will allow you to pause and replay and figure this stuff out over and over again. So good luck, happy calculusing, and I'll see you next time.